So, as Peter mentioned, I'm talking today about simulation for real-world robotics. And what we're going to be looking at is how can we take a simulated robot and bring it to real-world problems using either domain randomization or deep learning. And I'll be discussing a pipeline for how we should approach solving sim to real problems. Windows Update is always very convenient. So I want to narrow the scope of simulation because obviously simulation applies to so many different things. So I'm really just talking about robotic simulation here, solving robotic problems in the real world, and how to create a useful pipeline for real world robotics, and how to improve current existing pipelines so that they apply to more general problems. So first, when you're considering a robotics sim to real problem, you always want to choose your data set. What is the ground truth data that you're going to use for training an agent, for verifying that your application works correctly? Then you choose a physics backend that supports the particular problem you're trying to solve, whether this is Majoko, whether this is Habitat Sim, whether this is Air Sim if you're doing drone research, or even just video games like Atari. These are the general backends that you'll be considering for the problem you're solving. Then you want to define the controller that actually dictates the behavior of the agent in the simulated environment that also translates onto the real world environment. Then obviously you simulate what you're trying to test, have some metric to evaluate how it's performing, test it on real hardware or in a real environment. And this simulate test on real hardware becomes an iterative process where you evaluate it dictates how you update your simulation, dictates how you update testing on the real hardware until you converge on a solution to your particular problem. So why don't we do it in the real world? Why are we just looking at simulation? Well, one such paper did exactly that. They did 50,000 trials of randomly grasping objects on a table, over 700 robot hours of execution, and they had to constrain their problem greatly because obviously if it's really random, the robot could poke through the table and damage itself, requiring human intervention to fix that issue. So this is not feasible for every problem. This is a constrained space where we're really just looking at a Cartesian problem. This obviously, if we wanted to do more sophisticated tasks like stacking blocks or sorting objects or picking out things from an assembly line, this problem might get even larger, maybe even exponentially larger. So we really need to consider simulation here because as we want to do more sophisticated things, we want to be able to support those problems. Another paper was looking at using four robots in a real world environment to do simple tasks such as opening a door or moving to a particular position in Cartesian space. And they were able to train it in 2.5 hours to successfully execute the opening door task. Definitely a lot faster than the previous paper, but this problem is heavily constrained. It doesn't generalize to many of the problems that we might be trying to solve with robotics. And I'll be discussing some of those problems that were solved using most recent sim-to-real papers. So let's talk about some of the advantages and shortcomings of simulation, because obviously we want to be considering it, but it doesn't always apply. So simulation allows for rapid iteration. We can run multiple simulations in parallel, which allows us to collect data substantially faster than running in the real world. No risk to expensive hardware. Obviously, we can test robots, reset the environment, and nothing's going to break. Scalable across multiple machines. I can run a simulation on one machine, run it on one machine with lots of processors in parallel, and collect data very quickly. But there are disadvantages to simulators. There's a trade-off between accuracy and speed. The more accurate we want the simulation to be, that's obviously it's going to run slower. But if we want it to run really fast, we have to approximate how the physics interactions work. And so we actually run into an issue where certain physics simulators perform worse because they're taking those heuristic approaches to solving physics problems, which I will discuss later when I discuss simulation benchmarks. They don't always generalize well to real-world problems. Either the sensor accuracy using an OpenGL renderer is too accurate and gives you too much detail, or it just isn't representative of the real-world data that you would be collecting. and it's missing many sensory modalities such as tactile, soft body physics, not always formalized human in the loop descriptions of problems. And high-level APIs are required for faster iteration in software development. Right now, many physics simulators are actually finally catching up to where we need so that we can do rapid software development. But for the past few decades, since simulators came out even as early as the 1980s, they just didn't have that generalized software interface. We can solve some of these disadvantages or make them less of an issue using domain randomization, newer physics simulators, larger data sets, and I'll be discussing some papers that implement those and how we might be able to address problems in simulators to solve them. So I first want to start with that physics pipeline I mentioned from before, choosing a data set. Real versus simulated data. Real data allows the simulation to have higher realism, obviously. Sensors for capturing data has become significantly cheaper. RGBD cameras like the Kinect are much cheaper than they used to be. Time consuming to capture, however. So, a user has to walk through an environment manually. You need to collect lots and lots of data to match what you might be able to synthesize. And also, it's difficult to annotate. If I want semantic information for the polygons, you have to manually go in and label all of them. Simulated data is easier to randomize the domain because they're textured meshes. You can very easily change the lighting on them, change the colors, and you can have a much higher resolution than is supported by real-world sensors. So as I mentioned, yes, OpenGL can render at any resolution you want. So you can actually maybe downsample the image, subsample it, randomize, perturb it, add noise, etc. And meshes can be too perfect when compared to real world data. So they might be very extremely high resolution, which is not something you would see in a real world sensor. And also some object geometries are not able to be simulated, such as fluids or deformable objects. But there is one simulator that came out with a plugin recently that I'll mention that actually does support fluids and deformable objects better than you could before. So I want to talk about choosing a data set for grasping, sort of a specific example of where we might want to choose a data set. So we need high fidelity data set with diverse examples. We need household objects, kitchen objects. It needs to be related to the problem. We need to figure out how to reduce the data set we want to use. And for grasping, 4 data sets become immediately relevant. ShapeNet has many different objects of different object categories, 55 of those object categories. The meshes are textured. However, they're all simulated, and not all of them are relevant to grasping. Some papers have actually shrunk the meshes to be used for grasping, but how often are you going to try to grasp a car? How often are you going to try to grasp an airplane? So you would restrict the amount, but it's not quite the 51,000. YCB is a great benchmarking data set that has 77 unique 3D models. They provide a container full of those objects for anybody that's interested in purchasing it, and has 5 object categories for real-world household solutions, and they're also textured. The GRASP dataset by Jeanette Bogue has 280 unique 3D meshes, 87 object categories, and is generally used for different grasping benchmarks. It's all simulated, but it is untextured. Jacquard is another real-world data set, uses 240 unique 3D models, 8,119 hand-labeled grasps for those, so you can evaluate your own grasp planner against the Jacquard data set, and it is textured as well. So when you're evaluating these, do you need textures? Do you need objects that you're going to find in a household? Do you have to manually annotate these objects yourselves? All of these things come into play when you're deciding which data set you want to use. And here are the citations for those. So choosing a data set for navigation. We want to consider whether or not we need to use real world environments, whether or not synthetic environments are good enough and they translate well into onto the problem we're trying to solve, and if we can actually randomize the domain. Synthetic data sets, as I mentioned, are much easier to randomize the domain than something like Matterport3D, which is real homes scanned using an RGBD sensor in 3D. They took 194,000 different images, combined them into building scale meshes, about 90 different buildings, and they have 40 object categories to label the different polygons in the environments. These are great because they allow for easy robotic navigation. However, many of the surfaces are uneven because they are real-world scans, and they also include stairs, multiple floors. So you have to do some post-processing of the meshes so that they're directly related to the navigation task, unless you're doing something like drone navigation. For another synthetic data set, which has significantly more data, the SUNCG data set uses 45,000 different houses, 2,644 unique object categories, a subset of which would be relevant directly for, say, grass planting or navigation to a particular target, with 775,000 different rooms. Obviously, much larger data set. However, all of it is synthetic. So some of the meshes obviously are much higher resolution than you would get out of a normal sensor in the real world. So it's not always directly relevant to the problem because you need more realistic data. And the Stanford 2D 3DS, I wanted to mention here because it comes with semantic labels just like before. Has over 70,000 RGB images, 13 object categories, and 6 areas. These 6 areas are fairly uniform, so they allow for very simple benchmarking of different navigation algorithms. And the 13 object categories are obviously a very small amount, which basically allows you to verify, yes, my algorithm might work for some of these much larger data sets, which would take much longer to evaluate on. And here are the citations for those. Data set for UAV simulation. So we want to be able to train drones to operate through an environment. And so they took a tracking data set with basically a bounding box of an object that you're interested in and evaluated it on 4 different metrics that exist for 4 different algorithms for performing those tracking algorithms. So it's called the UAV 123. It's 123 different sequences of 110,000 frames provided with a benchmarking system. Bounding box and attribute annotation for each frame. So you actually have the category of what you're tracking and then also the bounding box of the object of interest. And they compared 4 different tracking algorithms, struct, meme, SAMF, and SRDCF. All of which are sort of outside of the scope of this talk, but essentially what they're doing is they're predicting the bounding box of the object. And really what I'm highlighting here is that data sets for doing UAV navigation exist, and these are something you want to consider, whether or not the bounding boxes are enough for the particular problem you're solving, or if you need to do something more sophisticated, like using the navigation data sets I mentioned before, which have obviously more object categories and let you do more diverse problems. Moving forward, we want to consider human in the loop. How do we actually collect data from users, which we can assume is generally ground truth? So how do we receive optimal training data? We can incorporate data from human operators into our training pipeline. We can actually evaluate whether or not they're performing well. Human-centered reinforcement learning is what it's been frequently called nowadays because it allows us to really focus on how does a human interact with the environment. And we can collect valid samples by virtual reality for teleoperated sensors, mass consensus through Mechanical Turk. I'll talk about a paper where they actually evaluated whether or not their algorithm was performing well using Mechanical Turk, and have a human operator perform the task correctly. So generally, this pipeline will start with collecting data from demonstration. So actually, ground truth samples of how we might want this algorithm to perform. One such paper, Deep Tamer, did exactly that. They were taking samples from human beings and training a agent to perform a specific action. I'll be discussing that paper in more detail later. Then we perform learning based on human evaluation. So instead of learning some kind of reward function, we have the user evaluate whether or not the agent executed an action successfully. And this can help inform how we might want to collect data from demonstration. Then we want to learn from that human evaluation, so actually design a RL policy based on an RL reward function based on the data collected from the evaluation. And then as we implement that, it feeds into how we might decide to collect more data or collect more evaluation data from users. And then finally, we're going to perform reinforcement learning on that, which again feeds back into all 3 of these. Oh, yeah, feeds back into all 3 of these because it allows, it's an iterative process. This problem is not well defined from the get-go. We have to think about how we're going to collect data moving forward. So I want to discuss Ross Reality because it's a great example of collecting data in VR. They're doing teleoperation of Baxter robot from MIT to Brown, and they had a simple folding task where a Baxter robot was actually finding optimal positions to fold a piece of clothing, which allowed the user interface to kind of take care of some of those latency issues by having areas to snap to, which restricted the amount of data you could collect, of course, because they're just simple Cartesian points that are discrete. But they were able to show that the agent was successful in performing the action that they had set out. So it was actually able to fold the clothes. And I really want to highlight this as a potential solution for future VR capture of data, which allows us to control robots in a first person point of view, which wasn't possible before cheap VR headsets came about. Crowdsourcing RL data is what the RoboTurk paper did. And what they were looking to do is specify a task, whether it's stacking blocks, grasping different objects, moving a block on a plane, and give those tasks to a user to evaluate. So that pipeline I was discussing before is exactly what they did here. They found examples from a user. They had the user demonstrate the correct action. Then they followed up by evaluating how those actions performed before, learned the reward function based on that, and then performed RL, and were able to show that yes, they can train an agent using Mechanical Turk and then correctly map that onto a real world robot. So they actually tested it on real hardware and successfully executed the actions. And they used 4 different input modalities: a VR controller, a phone, keyboard, and a 3D mouse. So they weren't just evaluating, can a user click through the environment, but actually, control a robot in VR, and it can be done remotely around the world.
How many people did they actually get to do it?
They got 2,000 people. So Mechanical Turk is very scalable. You can kind of just get as much as you want.
The people are actually they're controlling the virtual robot.
Exactly. So,
According to demonstrations.
So I want to talk about physics simulator backends that you might want to be considering when implementing your controller. So Dart is a commonly used physics backend framework. It came out several years ago. I'll talk more about the differences between them. Gazebo, Bullet is frequently used and recently has a PyBullet interface, which is much easier to use. Majoko is often used with OpenAI problems and is very robust. Open Dynamics Engine has been out for decades, but is kind of falling out of popularity versus Bullet or Majoko. And I wanted to mention PhysX, which is a very useful physics backend that is very accurate. However, most researchers aren't currently using it to solve their problems because it seems to be a Windows-specific application. Bullet is looking to use, instead of the Bullet backend, actually use PhysX, at least on Windows. So I wanted to mention to consider potentially adapting this to our particular problems because it's more accurate than the other simulators.
As far as I know, Gazebo doesn't have physics backend. It always uses either Bullet or ODE.
Yes, it's a high level. It uses Bullet, ODE, Dart, and it has it's
Gazebo doesn't have a physics.
It's a high level physics.
Physics backend.
Yeah, thank you for pointing that out. Yes. I want to talk about the different comparisons when you're evaluating these different physics engines. So obviously, the older it is, the more evaluation that it's been used. Different papers have considered using it. So something like Gazebo or ODE are decades old. Bullet being a little bit younger than that, and then Majoko and Dart coming out more recently. So they kind of learned from those other simulators. Virtually all of them are implemented in C, C++. All of them have some kind of C API, but very conveniently Bullet, and also Gazebo, which is a high-level interface for these other ones, allow for a ROS interface, which basically allows you to do C++, Python, JavaScript development on top of these existing physics backends. The contacts are different evaluation metrics, whether or not it's a hard or soft material that is being simulated. The solver is a mixed linear component problem. Complementary, I have it written down, sorry. mixed linear complementarity problem, solving linear equations to whether or not the objects are touching, and if they're going to collide with each other, if they're going to actually overlap, making sure that the positions are maintained given their current velocities. Majoko is kind of the weird one here because it's actually using a Newtonian model, a center of gravity model, and a projected Gauss-Seidel. I have slides for this at the end if we want to discuss it more, but I really feel like it's sort of out of the scope of this talk to kind of talk about the actual implementation details of the solvers. And then also of the contact models. The solvers, I'm sorry, the solvers. The integrator is really just whether or not we're considering just semi-implicit Euler functions, just those linear equations, or whether we're using RK4, which is the Runge-Kutta method. It's just a sort of a high-level Euler method that puts additional constraints on the problem. Again, I feel like this is out of the scope of this talk because we're really talking about simulation for real-world robotics. I just wanted to mention the backends here. One evaluation metric one evaluation test was the sim benchmark, and what they did is they had 7 different tests. So they did a rolling test where they actually rolled balls around a table. They had a bouncing test. They loaded a bunch of balls and then had them bounce. 666 and elastic 666, they just put 666 balls into a cube and then let them sort of move around. And they had ground truth for all of these different tests that they tested, that they evaluated empirically and evaluated whether or not the physics simulators were accurate and also how fast could they perform these simulations. So I wanted to just show a visual of the 666 test, and they really just load that cube up, drop it, and see how the balls move throughout the environment. And then they wrote a script that actually generated the positions that the balls should be at and evaluated how they moved through the environment. They also they were comparing all of these against their closed source unreleased simulator as well. I didn't mention it here because it's unreleased. And they also considered that sort of more ground truth. So there is some impetus to make the other simulators look worse than theirs. But I thought these were really good tests for evaluating whether or not these physics simulators are performing actions accurately. And what they really evaluated is whether or not these simulators perform the task successfully. They have this sort of qualitative metric of plus, 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 but the actual online webpage has more quantitative metrics, and there's just a lot of them. So I'm happy to show that at the end of the talk. But what I wanted to highlight is certain problems are not actually able to be solved by these simulators. So Majoko could not do the bouncing test or elastic 666 because of how it's calculating these objects next to each other. It wasn't really handling elastic collisions very well. ODE couldn't really do the rolling test because the objects wouldn't really roll on the surface as they moved the table below it. And I can show more images if you guys are interested in that. And some highlights that they pointed out is Dart's simulation pipeline is not suitable for simulation scenes of multiple objects because it's very slow when you add multiple objects. Bullet has severe position level drift, meaning that their solver method is actually, the time step between positions is too inaccurate. So when it's actually predicting the next position, you get significant drift as the simulation runs longer. Majoko's soft contact model cannot control elasticity. So that's what I mentioned here is these tests weren't actually usable. And then Majoko has consistent slip, which requires some additional post-processing to make sure that your model is performing accurately. So really what I'm highlighting here is each simulator has its own pros and cons. And when you're considering your problem, this is a nice chart as to whether or not that simulator supports the problem. And then you also want to look at the high-level APIs, whether or not it's usable. So one thing I wanted to mention is a lot of these different simulators in their papers were talking about the lack of soft body physics simulation. So there's one such simulator called SOFA that was able to write a plugin that actually does handle geometry and simulation of soft body robotic hands, and also snake-like arms that have multiple different points on it and can actually handle sort of a perturbing of the robotic arm. The problem with this, of course, is that it's closed source. So it means that we're not really able to utilize what they've written for this problem. However, their paper is obviously readable. So I want to point out that looking forward, we might want to integrate this with existing physics backends to solve specific problems.
Is the license prohibitively expensive?
You can download it and use it, but it's a binary. So it's not a license. You just can't decompile it because it's written in C and C++. So it's
even Boolean or something. I mean, at this point, these are so advanced that you use them as a black box anyway. I don't think you're gonna start digging into bullet code anyway. So I don't know if this is necessarily a showstopper. The fact that you don't have access to it.
Have you used a simulator with your own continuum robots?
No.
Okay.
it's more just pointing out that somebody has written a modern plugin for soft body simulation. I agree, most people aren't going to dig into PyBullet. However, researchers could technically take this paper and implement it into an open source platform. So I want to talk about domain-specific simulators. Obviously, this talk would not be complete without mentioning Graspit and OpenRave, two simulators that have been heavily developed for doing trajectory and grasping simulation. Graspit is a very flexible framework. You can write multiple plugins for it, and obviously plan grasps very conveniently. OpenRave has a very flexible trajectory planning framework, and many people have written trajectory planners or grasp planners in this framework. And I'm really just highlighting that, yes, there are domain-specific simulators for handling these more bespoke problems like grasp planning and trajectory planning. Simulators and high-level APIs. So for navigation tasks, very recently, simulators have come out like Gibson that handle moving through an environment that looks photorealistic, and it supports that Matterport and Stanford 2D 3DS datasets that I was talking about before, and goes up to resolution of 512 by 512. It's written in C++, so it's very fast. Minos is a simulator that came out a little bit earlier, written in JavaScript, so it's a bit slower, but it has support for arbitrary resolution and supports both Matterport3D and SUNCG inherently. Habitat Sim is a new simulator that came out very recently. Earlier this year, I think April 2019 is when they actually published the code. And it supports Matterport3D and SUNCG inherently, supports 10,000 frames per second, so very fast simulation, and also has this 512 by 512 resolution. This is supported by Facebook, so this is being actively developed. And really what I'm highlighting here is that these are brand new. These haven't been heavily evaluated yet because they're so new, but these are definitely simulators that we want to be looking at moving forward for navigation tasks in robotics. And the fact that they support these large data sets inherently makes it very convenient for us to introduce our robots into these environments. One interesting thing I want to point out is the Gibson environment actually supports mapping these simulated images onto real-world photorealistic images. So as you can see here, there's this large black mound. This is a hole in the rendered image. So when they captured the environment, it didn't get absolutely every single polygon that it should have, and they didn't go in and fix it. So what Gibson wrote is a style transfer algorithm that takes the photorealistic image that you would expect from the environment and mapped that onto the RGBD image that's rendered by the simulator environment, and was able to fix most of these holes both in the RGB and the depth image. And I think that Gibson offering this is great. I think Facebook should definitely look to integrate that into their own simulator. And when we're also considering domain randomization problems or trying to generate photorealistic data, this is an interesting solution that's kind of lightweight. I have to mention drone simulation. AirSim is obviously the one to go with. It handles both vehicles and drones, and they're using synthetic environments that come for free because many people are using Unreal Engine to generate lots of game environments for driving and drones. And they're able to get fairly realistic looking images from this with semantic labels, because they're all semantically labeled in the mesh types for these different environments, because developers are really making much more rich meshes for their particular games. And they plan to use the PhysX engine in the future, but currently they're just using Unreal Engine's basic physics simulator. So you can expect this to get more accurate as time goes on.
Is there any collision detection going on in here?
Yes. Yeah. I mean, as you can see, the car's driving. It's not that it's just moving in 2D space. It's actually testing the simulation. It will bump in and actually fall backwards like you would expect a drone to. It's not perfect, but it's pretty good. I want to talk about how we can use deep learning to speed up simulation. So a lot of these simulators, they're using heuristic methods. There's a bit of a slowdown in the simulation. And we want to actually speed up. We want to make it go faster. So learned simulators have this deep learning advancement. There's a lot of high-level APIs for doing deep learning now. And we can consider using deep learned methods to make these processes go faster by creating learned representations of the worlds that we're actually simulating. We can also use learned engines for faster simulation of just world mechanics, for state space transitions. Really, there's a foundational paper I'm going to show that did this very recently for 2D games, but I believe that this can be used for robotics as well. And so I'm just going to highlight World Models, which is a very well-written paper where they took this very simple racing game and Doom, created a MDN-RNN, just basically a simple recurrent neural network architecture that figured out, okay, here is the input image. They trained a variable autoencoder, which is just an autoencoder for compressing, creating an embedding of that image. Trained the recurrent neural network to take that embedding and predict, based on the input of an agent or a user, what the next state of the simulator will be. And then actually feed that into either the environment or this world model to actually execute different actions.
What's MDN?
MDN, yeah, that's it. So they're really just mapping the action and state of the simulator onto an RNN architecture. An agent can then learn how to control the avatar using this learned representation of the world. So we're actually able to train models in this much faster representation than we could otherwise. And it allows for rapid learning in a physics environment. They tested it specifically with Doom, as I mentioned, and it's faster. That's really what I'm highlighting here. A differentiable physics engine recently came out, and basically what it allows you to do is every single component in the physics simulator is differentiable. The position, the textures, the joints of the robots, everything has a differentiable function associated with it. And that can be incorporated into both the forward and back propagation algorithms for robotic learning. This means that we can perform fewer steps in our learning algorithm to train robotic agents. And it's just the physics state and textures can be integrated into either the reward function or actually the convolutional neural network for our learning algorithms. So I want to mention Deep Tamer because it was a very good paper for speeding up simulation. They basically took human in the loop data from a environment, in this case bowling. They had a human operator control the bowling agent, collected that as ground truth data, and used that to seed a reinforcement learning policy, which they then trained on its own to perform the task better than the human operator did. And really, because they used the human actions, they could simulate less. So in 15 minutes, they were able to train an agent that performed just as well as reinforcement learned agents would at 15 minutes, they would eventually reach the same performance, but it took a lot longer. And the human operator only had to play for 7 minutes to collect that ground truth data. So I'm highlighting this because we can reduce the time spent in simulation by using this human in the loop ground truth data for learned representations. Sensory modality. So I want to mention that physics engines have this lacking implementation of different sensory modalities. They all have some form of RGB rendering, but less common things are depth rendering. So they're using OpenGL to approximate depth rendering, but actual ray tracing depth rendering isn't always implemented. Actual structured light sensors aren't usually implemented in these physics simulators. And while OpenGL depth rendering is usually good enough, it's not going to give you the same resolution in the real world. Semantic labeling comes from manually annotating different images. Tactile it's kind of bespoke for the different robotic arm you're doing, so they approximate it by just checking if it collides with something, and that's not always going to be the same as the real world. Accurate force models, as I mentioned, those physics simulators have problems handling either elastic collisions or rolling physics. So we have to consider that maybe some of the force models aren't going to be accurate. Sound is usually just completely missing from these simulators, and that might be an interesting thing to look at. And human in the loop hasn't been formalized. So how do we actually consider using that in our physics simulator paradigm? It'd be nice if there was some kind of interface for collecting that data from input. And so lacking these sensory modalities does not mean that these physics simulators aren't complete. It means that we have to consider them as a trade-off when we're evaluating which ones we want to use. So we want to improve the sim to real fidelity. We want to actually create more representative data. So GANs allow for better grasp generalization. A paper by Jeanette Bogue took YCB objects and generated geometry based on the initial seed geometry. And they tested their results using a grasp planner that learned on the whole data set that they generated and the YCB object data set, and just the YCB object data set alone. And they were able to find that their agent performed significantly better when it learned on this domain randomized object geometry instead. And so this is a very good way to take a real world data set, generate synthetic data based on it that might be representative of all our objects that you might want to see, and actually either evaluate our framework or train a more generalized model based on that. And I want to point out that they used the GAN, which as of 2014 has been really popular for generating different either images or 3D geometry. Photorealistic video synthesis. So what they did is they took a semantically labeled image in a simulator environment, a style that they wanted to emulate. So you go out to the road and you take a picture where they have a data set of different roads, and took that semantically labeled image, trained an agent that would actually take this, the style you wanted, and create an image based on that semantic mapping of what you would sort of expect given the style. And so what this allows you to do is you can take lots of different style seeds and produce a much larger data set that is randomized to generalize to these different specific situations. It's 2048 by 1024, which is a very high resolution for multiple different problems. And using these simulated data sets, we can perform style transfer very quickly. It's just a really good way for mapping that simulated data onto real world data. And I wanted to mention this paper, which is very similar in how it's implementing this. But what I wanted to highlight is they also created a very convenient user interface for selecting different style inputs to seed the network. So examples of robotic simulation pipelines. So we've talked about acquiring data sets, we've talked about physics engines. How do we evaluate whether or not these different papers implemented these steps that I've talked about successfully? So CAD2RL is a drone simulation where they took a monocular view of a real world captured data set and moved it through an environment, basically just finding for each of those frames, where do I want to navigate to next, given a position in the environment that I want to navigate to. So they trained it on the environment itself. And then I just want to show this. Okay, it's missing a GIF. That's weird. Okay, so there's supposed to be another GIF here. I can find it later, but basically they tested it in the real world. I can pull up the YouTube video if you guys want later. But they tested in the real world that basically they just had it navigate, and it was successful about 94% of the time for navigating to a specific environment. Initially, they tested it and they got 70% accuracy when just testing it in the first place. But once performing some additional RL in the real world, they were able to get much higher
So
accuracy.
was the test on the same environment or different?
Different environment.
But the key with this paper, right, was like they trained it all in simulation because of the domain randomization. Like it gave it the generalization.
Exactly, and it's also much faster to do that learning rather than just throwing a drone out and having it collide with walls. They also ran these tests as soon as it collided with a wall. They heavily punished the simulator, and they only really rewarded it when it performed a trajectory successfully.
Do you know how much training time they needed on that?
They had 120 hours, if I'm remembering correctly. It's in the I can double check the paper, but so a paper I'm sure Matei is familiar with was using pose detection to plan grasps on objects in an environment and then actually execute those grasps. So what I'm highlighting here is it's real data to simulated data to real data again. And what we're doing is we take an initial point cloud, we approximate the geometry that's at that particular position, and then find candidate grasps using GraspIt in simulation to actually manipulate the object, and then in the real world test those grasps. And so I want to highlight that we don't need to just do sim to real. We can actually do real data, simulate how we want to perform the action, and then operate on the real world again, and then evaluate whether or not we were successful. And for this, they chose a representative of household objects data set that they happen to have meshes for. 25 different household objects, and then they also had 45 extra 3D models. So again, they chose a data set that was representative of the problem, defined the controller, and executed it. Another paper, Peter would be familiar with this, where they did folding tasks. They took a 2D image of a piece of clothing, turned it into a mesh for a folding action, and in Maya simulated the folding to make sure that basically it was able to fold the different pieces of clothing. They used that 2D mesh to find optimal positions to actually execute the folding action, hooking to those different points on the polygon describing the mesh, and then executed it on the real hardware. So again, real to sim to real example of a good pipeline that worked and also defined its problem and constrained it appropriately to solve the problem. A paper that I wrote recently took two modalities of input, both RGB and RGBD, and then also tactile data collected from the occluded side of the object, and was able to predict geometry of those input point clouds. And so what I'm highlighting here is we don't need just real to sim to real using just one sensory modality. We can take multiple to solve these problems and approximate geometry better and more accurately for the physics simulation to perform better. I didn't mention, we were using GraspIt to perform the grasp planning in simulation and then executed those grasps in the real world. And we trained the model using synthetic RGBD point clouds and also synthetic tactile touches on the occluded side of the object. So there was no real data collected for training this particular pipeline.
Can we just
Yeah, go.
Sorry, so like this is a paper that I saw on a workshop this year, so it's very recent. But it's very similar to this, or some previous work that you mentioned, where like using like these style transfer techniques to take the simulated environment and try to make it more realistic, like Gibson does. What they did was they took they trained the robot in simulation, and then they just took real images and learned to make it more simulated, like to match the simulated.
So they downsampled the real in a sense.
Yeah,
the simulators, they back into the simulator.
Exactly, and then the robot just basically operated in the simulation the entire time. Who was this? I forget I can probably find it, but it was on workshop.
There's another paper that came out March this year. They were doing sim to sim and then sim to real. So they mapped the simulated image onto a simulated image and then mapped a real image onto the simulated image using domain randomization. And then that offered a much more realistic grasping simulation because they were just operating in that simulated image environment. I would have included it, but I literally found it this morning, so I couldn't do it justice. But it's definitely something to look at. But this came out 2 months ago, so how much does it really solve the problem yet? But yes, that's probably where this paper would go next. Is taking a look at how can we better handle more generalized problems. Learning dexterous in-hand manipulation was taking a look at a shadow hand. And they constrained the problem to a smaller vector of just discrete actions to actually move the cube, and tested it solely in simulation, just using an RGB image, and they randomized the colors associated with the shadow hand itself. And then we're able to show that, yes, once it trained this agent, they could perform this in the real world without any additional learning. But what I want to point out is that constraining the problem the way they did doesn't necessarily generalize to lots of different problems. They're just moving a cube in the hand. They're just looking at whether or not the correct face is showing. This isn't, a stacking task, but it is a nice example of how we might formulate different sim to real problems, randomizing the colors of the meshes, randomizing the different types of faces you would be looking at, and then actually manipulating an object, and perhaps I'll talk about a modular system. We could use this as a particular module in a much more complex solution. Another paper used by Jeanette Bogue was using action primitives to train an agent. And basically they had a peg and hold task that was just trying to figure out in Cartesian space, how do I actually place a peg in a hole? Very simple, but they were able to show that using these action primitives, there was just a zero-shot translation onto the real world because they randomized the domain of the input. They changed the colors, the textures of what the camera was able to see so it could handle a more general problem. And they also constrained their problem to a much smaller space, so it was much easier to do this. And the agent had to figure out what type of peg it was just using the RGB alone, and also the force model of the robotic arm. So they actually didn't just take the force model into consideration. They tested just the force model, they tested just the RGB, and then they tested both. And the both performed better and was able to figure out how to actually put that peg in the hole. So in this paper, they were taking a modular system. They were doing an object detector, grasp proposal system. If you need the title of that paper, it's Making Sense of Vision. So it'll be in M. It's alphabetical. Oh, got it. Okay. They were doing zero-shot transfer, basically taking these different modules that were trained to successfully execute the action. They sort of put them together to solve either a grasping task or a sorting task. So using the object detector, they were able to find the bounding boxes of the objects, and then using those particular bounding boxes, were able to find grasp metrics where a system was trained on taking an image and finding optimal grasps, and another system was trained just to find bounding boxes. And then they found that there was a zero-shot transfer onto the real world. So they didn't have to do any additional training to make sure that the agent performed the action in the real world. And so just to talk about looking ahead, where these things can go. So we want to consider different ways of simulating soft body physics in more general purpose simulators. Yes, it's not specific to every single problem. Yes, it requires serious dev time, but it can be useful potentially for just simulating tactile sensors. It doesn't need to be hyper-realistic soft body physics simulation, but that paper I highlighted might be able to enhance our ability to do tactile in simulation. We need larger data sets of real world scenes. So even though Matterport3D and YCB are generally representative of the problem that they're solving, or even Jacquard, they're not nearly as large as these synthetic data sets. So using domain randomization, we can create much larger synthetic data sets based on that initial seed input of those real data sets, but it's not necessarily ideal. So how do we maybe train an agent to automatically go out and collect that data for us in the real world? And then we also need high-level APIs to be more accessible. Habitat Sim is a step in the right direction. ROS 2.0 and MoveIt 1.0 are a step in the right direction, but they're not solving the problem yet, and it makes it harder for us researchers to do development very quickly. And then also a lot of the research is disjoint, so we're not really able to necessarily directly integrate what exists into our current work. PyBullet is currently developing a plugin for VR, and Unity has support for VR. Unity also has support for ROS. So there is sort of a momentum to create a formalized representation for VR, but something to look for is how do we more accurately and conveniently collect data from human users using cheap VR headsets. Valve is coming out with a new headset that uses this knuckle sensor, which actually gets finger position based on whether or not you're touching a sensor. Much more useful data, literally coming out next month. So
Can we buy that sensor?
it's coming out next month,
Okay.
and it's $1,000. So we need to talk about it. ROS 2.0 and MoveIt 1.0 is looking to solve simulator integration into deep learning tasks, looking to use OpenAI GIM as a potential way to plug in directly into many existing papers, just by simply switching the physics backend. So they're really looking to get better integration, but it's not quite there yet. So that's something we want to look at, as Majoko, which is typically used for OpenAI, is a very good framework. It's closed source and can often lead to some development headaches when making sure you have licenses on all of your machines. Better domain randomization techniques. So it'd be nice if TensorFlow maybe had the ability to sort of provide an interface for convenient domain randomization. Better and easier to use APIs. OpenAI is a step in the right direction, and industry support is increasing. So Facebook has Habitat Sim, Microsoft is directly supporting ROS and therefore Gazebo, and different robotics companies are getting lots of funding that obviously use these open source tools. And also I want to mention creating custom sensory modalities is a lot easier now because of these high level APIs. So we might want to look at how we can integrate those better and devise different solutions to solve our particular problems. GANs and domain randomization produce larger data sets. So as I mentioned, that we're able to create these synthetic data sets. And using deep learning for speeding up networks is new and should be researched further. So actually taking these taking this learned representation of the real world, or actually integrating a differentiable model of our physics engine, is a good way for evaluating not only the effectiveness, but also speeding up our learning process by either reducing the number of steps or speeding up the way we can simulate. And that is my talk. Thank you.
Okay. I think we'll take some questions from the audience if there are any. Enrique, hello. No questions from the audience? Okay, then we're going to ask the audience to grab some food and leave. Okay.